The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. Thanks for joining us on the webinar today. Before I introduce our speaker, just a quick introduction on myself and Alliance Corporation. My name is Gerard Solano, Director of Technical Sales Canada, based out of Mississauga, Ontario. I share responsibilities over our carrier customers and supporting contractor communities, both macro and in-building projects. Alliance is a leading distributor of wireless infrastructure products, providing supply chain solutions, technical expertise, and extensive inventory of all infrastructure needs. We consider ourselves as an innovative market leader with several firsts in the fiber-to-the-tower application. Our headquarters, as I mentioned, is in Mississauga, Ontario, where it's both a stocking, manufacturing, assembly facility. We also have facilities in Calgary, Alberta, a sales office in Montreal. Our reach is North America-wide, where we also have distribution facilities in New Jersey, Denver, Mexico City, and a manufacturing facility in Juarez, Mexico. Alliance is CommScope's channel partner in Canada, providing distribution, stocking, reselling, and value-added services along with other supporting products. Our presenter today is CommScope's Vice President of Strategic Marketing. He has over 15 years of experience in the telecom industry with companies such as Allen Telecom, the old Andrew Corp, CommScope today, and 10 years prior with Texas Instruments. He's led the wireless industry in adopting many antenna system innovations, including RET, remote electrical tilt technology, and pioneering the concept of agile networks, which form the basis for current initiatives in self-organizing networks. Without further ado, I'd like to hand this off to Mr. Philip Sorrells.
Thank you very much. I appreciate the introduction, and as always, appreciate the opportunity to be with our friends and partners at Alliance and speaking to your affiliates and customers and associates in Canada. You know, on the side, I'm really looking forward to the next 3 weeks. I have a vacation coming up in Vancouver. And it's been a while since I've been in British Columbia. I'm really looking forward to it. We have had the privilege and really the opportunity to work with some of the world's largest LTE network build-outs. As you can imagine, with our position in North America as the leading supplier of RF products into the North American market, we got the opportunity to jump right in the middle of the biggest LTE build-outs as they were happening. And depending on your perspective, we learned a lot of things, sometimes the hard way, right? So what I'm hoping today to do, and hopefully it'll add some value to you as you think through your LTE implementation strategies and work on some of the unique issues that happen there. We're going to give you some lessons learned and some of the best practices that we have experienced, again, sometimes the hard way, in implementation of LTE. So I hope you'll find this interesting and useful, and we look forward to collaborating in the future as you take on these challenges. So first, a little bit about who we are. Again, CommScope is a leading supplier of broadband applications in many, many, many markets. We serve enterprise businesses with data centers. We're one of the largest suppliers in the world of structured cable solutions, certainly in the telecom space with our fiber to the home type products and services. And many of you that are in the wireless industry would know probably very well the Andrew brand, and that is the wireless division of CommScope. And as you can see here, we have a broad portfolio. We're the #1 supplier of microwave backhaul antennas. We've been doing that since, I don't know, 70 years, so a long, long time in that market. We're the leading supplier today of small cell DAS type solutions. We also are the world's largest base station antenna supplier today and provide a whole range of RF conditioning devices, splitters, tappers, interference mitigation filters, duplexers, diplexers, TMAs, basically all the RF infrastructure that makes the antenna system work and work well. So that's really our perspective. We You know, our value prop to the industry is that we are everything but the radio, and our core competency is in RF. And so hopefully you'll see some of that. And that certainly is the perspective of what I'll talk about today, is the RF path and very practical, get your hands dirty type working stuff. It's kind of who we are. So the first thing is, I certainly am not going to bore you with marketing material that you've seen over and over again, but there's really something important about this part of this presentation that hopefully everyone in the audience will really understand and pay attention to, and that is this. 1G and 2G technologies were designed for voice. They were designed for a voice system. And 3G, or wideband CDMA, was designed primarily for voice, but also with consideration for internet protocols, data considerations, multimedia, text, and internet. And really, 3G was the first mobile broadband system. LTE is designed for data, with voice as a secondary consideration. Now, that's important to really keep in perspective as we go through the rest of the presentation, because hopefully I'm going to reveal to you some of the things that happened to us when we used the same run rules that we used back in the 1G, 2G days to think through how the RF environment should be built for 4G. And guess what we learned? We learned that those run rules aren't the same. And we ended up with of course, our customer partners in situations where we looked at what we had done and said, wait a minute, we used the run rules for designing 2G to do this LTE design, and we ended up needing to do some things differently. So very important just to keep that perspective. 2G is designed for voice, 3G is designed for voice with data, 4G is designed for data, and it has some very significant ramifications. The other thing to recognize, and I'm sure all of you already recognize this, but the biggest value in LTE are the very sophisticated subscribers who have already decided to buy an upgraded handset or device, a smartphone or a tablet. So those are the customers who typically are very sophisticated users. They use the vast majority of data, and they're willing to pay more. So that's a premium subscriber. Now, this survey done by Ericsson in June of 2013, and by the way, they've done this survey again, and the data is very much the same. But that survey says that for those intelligent, sophisticated buyers, the premium subscribers, about 20% view the quality of the network as one of their #1 differentiator for how they choose who they place their subscription dollars with. The network performance. Again, this is a sophisticated subscriber. You know, my 26-year-old son is a good example. My 26-year-old son, who's not in the industry, by the way, knows what LTE is. He did the research. He wanted to find out. So the network quality is very important. And of course, they expect high value for their money. So they, if there's not good signal strength, or if there's not good data download speeds, they're going to look at that device and question why they invested their hard-earned money for that. So it's really important. That says you got to have better network quality. That says you probably are going to have more cell sites, and that ultimately, and we'll talk about this many, many times in this presentation, it says you have to have better SINR, system signal to interference noise ratio. So LTE drives capacity, or capacity is a requirement for very sophisticated LTE systems. And this chart really goes back another 50 years before the time this was presented. This data was actually presented. But what this says is there's 3 ways, fundamentally 3 ways to get more capacity. out of any network, any wireless infrastructure. One way is to add spectral efficiency. Now that basically means upgrade the air interface technology. So 2G was an FD type technology, CDMA technology, then we have wideband CDMA technology, and now we have LTE technology. Those are the air interface. The good news is, what's really phenomenal is if you take the quality of the radio technology that's available today in LTE, it is truly cutting edge technology. Absolutely almost to the theoretical limit of Shannon's predictions on capacity efficiency. We'll talk more about Shannon's Law later. But we're really at a point now where the spectral efficiency of the radio technology that we have today is absolutely spectacular. So the second way to add capacity is adding more spectrum. For those of you who are dialed in, you'll know that at the beginning, North America, in the beginning of the wireless revolution, we had 800 megahertz. Then we had 1900 megahertz, and then we have 2.1 gigahertz, and now we have 2.5 gigahertz, and there's 2.3 gigahertz that is talked about, and there's 900 megahertz, and now there's 700 megahertz, and in the U.S. market, there's discussion of 600 megahertz and 3.5 gigahertz. So adding all this additional spectrum is another way that we can add capacity. It opens up radio resource, it opens up bandwidth, and that is the second way to grow capacity. But the number one way, by far, the biggest way, the most historically dominating way of adding capacity is densification. Densification is a term that says that we've added more cells or we've split existing cells into different sectors. So again, going back to the beginning, in the beginning we had omnidirectional cell sites. So we took the big, large omni cells and we split those into 3 sectors, and then we added more sectors and we split those sectors again, and that is the dominant way that capacity is added. So these 3 things are important as we look at how we now roll in the LTE technology and what this means to building LTE capacity. So LTE is an interference-limited system. LTE is an interference-limited system. And what's important to realize here is we go back and talk about Shannon's Law. Shannon's Law basically says the capacity of any system is limited by the noise in the system. And again, I referred earlier to the performance characteristics of today's radio technology. Today's radio technology literally is at the edge of the limit of Shannon's prediction models in terms of efficiency of that air interface. So to really maximize the performance experience in LTE, you have to focus on interference mitigation. And as you can see in the illustration here, the key question becomes the user experience at the edge of the cell. Now, ideally, if in a perfect world, if you're a mobile operator in a perfect world, the users on the edge of the cell, if they had performance issues, you just ask them to move closer to the cell. But that's not the real world. The real world is they are where they are, and their experience is going to be defined by what happens at the edge of the cell. So it's important in the design of an LTE network to not look at the close-in cell site, but to look at the edge site, the edge of the cell, and that really defines ultimately the experience that the user community will have. So 2G versus 2G, 3G versus LTE. Again, not being familiar with the entire audience there, I can tell you that from my practical experience in the industry, when I was involved with 2G and 3G network design engineers, their number one KPI, or key performance indicator, the number one metric was RSSI, or signal strength, which made sense because we were building a voice network, and initially, certainly in the early days of 2G, aiming at maximizing coverage. So it was very important that signal strength defined what we decided was good. LTE, again, being interference limited, is significantly different. In LTE, the key KPI, or key performance indicator, is really the SINR. So as your network planners design a layout of cell site structures across your network, the parameter that they need to look at for your existing 2G and 3G system is RSSI, or signal strength, but as they evaluate the right approach to build the LTE network, they're looking at a different parameter, signal to noise interference ratio. Now that affects a lot of things, and certainly one of the key things it affects is the strategy for selecting equipment, what the right antenna technology is, what the right positioning strategy is on cell towers, what the right positioning strategy is for small cells. All those become very important parameters, and it's important, just a radically important thing to understand the difference between designing for signal strength and designing for SINR. Why is that important? Well, we hear over and over today, it's very common in the industry to talk about LTE Advanced, even though a lot of us are still implementing LTE 8. A lot of the discussion that's in the industry today is LTE Advanced. Here's something a lot of people don't really realize. Virtually every LTE Advanced feature requires a noise floor, or a SINR, that's significantly more demanding than most current networks can provide ubiquitously across the entire network. Now, I'm not saying that in some clusters and cells that this SINR level is not already achieved, but ubiquitously across the network, there's still a pretty good gap. So that's important to realize, because as you develop a strategy for implementing advanced technologies like MIMO, or carrier aggregation, or COMP, or any of the, or very specifically VoLTE, you really have to evaluate the ubiquitous nature of the network and what noise floor you're actually able to achieve, and then take advantage of some very simple, hopefully simple, but some key things that can be done in the RF path to get significant improvements in the noise floor. Here's a good example, MIMO. So as you can see in this illustration, even in an indoor application for a MIMO implementation, you still need about 10 dB better SINR than you would need in a 2G or even a 3G application. So inside an in-building application, finding ways to improve your SINR about 10 dB is relatively simple. Think about that as you think about outdoor cell sites. It's a lot harder to find 10 dB SINR, especially when you look at the reality of many cell sites. On slide 10 here, I'm showing an illustration. This is common. It's not uncommon at all to find outdoor cell sites that are surrounded by many, many different kinds of apparatus, lights, air conditioning vents, other steel equipment in the environment. All those things contribute to noise, and can be quite difficult to overcome to achieve those types of noise floor levels that are essential to really take full advantage of LTE. So how do we overcome some of the complexities? Well, this begins the story of how you add LTE to existing cell sites. So I know, for example, in Canada, 2G and 3G is the dominant technology. It's paying the bills in many applications. It pays for the bills of your business. So as you add LTE, the question becomes, how do I add LTE into existing cell sites without interrupting the performance of my existing paying the bills technologies? So that then creates some complexities, like multiple spectrum bands. How do I take LTE at 2.5 gigahertz and implement it on a cell site where I already have LTE or 3G running at 2.1 gigahertz? what happens when I launch 2G, 3G, and LTE out of one antenna face, it using a multi-band antenna. What trade-offs do I need to make? How do you protect the current system so that you minimize downtime, right? You take down a whole cell site to add LTE. How long is that cell site going to be down? I mean, I've heard horror stories, absolute horror stories of cell sites being taken down to do a simple LTE update that then went for weeks, and in fact I've heard stories of months of the cell site before it came back online to provide basic service. So a very critical thing. And then once you make that time and effort to climb a tower to add new technology, what can be done to minimize rip and replace and having to do it again in the future, and ultimately it's time to market. For those of you who have LTE today, you already know you're not going back. I mean, the LTE experience, when it's done right, is truly transformational to the user. I have it. Even at my home, I keep my Wi-Fi turned off because the LTE experience is just so much better. So he who gets there first is going to get the lion's share of those sophisticated users who are willing to pay a premium. So time to market is very critical. So there's some key considerations that should be thought through as you plan. I've already talked about signal strength versus SINAR, so I'm not going to talk about that again. I've already kind of gotten into that. But the next one is grid lines tend to devolve. So for those of you who are RF, have an RF background, and for those of you who don't, that's okay. But 2G technology was designed to be so that cell sites stayed in grid, right? So you would have the alpha sector gridded to the alpha sector of another cell site, gridded to the alpha sector of another cell site. Why? Because in those type of technologies, GSM in particular, frequency reuse is a really important parameter. So staying on grid became a pretty important consideration to think through as you design GSM. 3G, wideband CDMA technology, the grid is still important. You still have some characteristics of the performance that require that type of grid, but it doesn't have to be as rigidly applied. And the grid in LTE, again, is a slightly different consideration as well. In fact, in many LTE applications, we're taught to align the grid to the user. So there's considerations as you think through how the physical implementation of your RF happens with respect to what trade-offs and when to make them in terms of letting your grid line devolve, move away from its original characteristics defined by your first generation 2G network. Third consideration here is ideal azimuths. So way back in the beginning, when we went from an omnidirectional antenna to our first set of sector antennas, the first set of sector antennas used 120 degree or 90 degree azimuths. As we moved into 3G, the ideal azimuth became about 65 degrees. And today, I would say that most LTE antennas use about a 65 degree azimuth. But I can tell you this, what we see in the industry is a continued move toward even tighter azimuths, 50 degrees, 45 degrees, 30 degrees. And I'm going to talk about why that is in a later chart. So we'll cover why we start to see the azimuth beam width in LTE systems move to more narrow, even more narrow than 65 degrees. The fourth thing here is performance specs. When the original 2G networks were built, the key performance spec was gain. If you took an antenna system, the key parameter was gain. Back in the early or in the late 90s and early 2000s, when many of the 2G and early 3G systems were implemented, the antenna technologies themselves didn't require a PIM spec. Passive intermod was not even specified. And today, of course, passive intermod is a very, very crucial spec, and one that, you know, we have questions from some of the people who registered for the event earlier on PIM. So it's important to consider then this last thing of age. You have existing cell sites that have existing 2G or 3G network equipment on them. That equipment may have been designed and built in the early or mid 2000s. Some of it may still be up there from the late 90s. They were designed at a point in time when the performance characteristics were substantially different than they are today, and they could create problems for your new LTE network. So it's important to look at all those 5 characteristics and see which ones could be affected. Now the pie chart talks about weight and wind load, complexity, and reliability. Those considerations are really highlighted when we also make the additional move of moving the remote radio head to the top of the tower. We take that remote radio head from the bottom of the tower and put it up at the top, close to the antenna. There's some real benefits. You reduce loss. You reduce loss, you get better gain. You get better gain, you get better sonar. That's a good thing. But now it adds some complexity. It adds weight and wind load, complexity of many more connections that have to be made. And now at the top of the tower, you have an active component that has a different reliability curve than many of the passives that we typically see at the top of the tower. So all these things have to be considered early on in the planning. Trade-offs need to be thought through and managed and predicted. So the next slide here is just has a little bit more detail on the technical evaluation of the technical evolution. I've talked about much of this already, so I won't spend a lot of time on this. Some discussion here about greater need, for example, with backhaul. As you add capacity to the front, you got to add capacity to the back. So, you know, if you plan out your LTE network and underclub what kind of backhaul to add to it, then your overall network won't be balanced. So just another consideration there. This next slide shows just a really simple illustration of the level of complexity change. So this on the left-hand side is just a simple illustration of a typical GSM site with, you know, 1 cross-pole antenna per sector. Now we evolve to a site that's got GSM and wideband CDMA and LTE. We go from 1 simple antenna per sector to 3, maybe 4. We add radios at the back, and you can start to see just a considerably more complex implementation that really has to be thought through. The next thing is the weight and wind load. This is a great illustration. Our engineers put together this. It's a compilation of observed information as well as some predicted information. But there's 2 lines on this graph. One, the darker blue line is the equivalent weight per sector, and the other line is more, the EPA is more or less the surface area that catches wind in a network. So those are really important considerations, and you can see that as we evolve from 3G to now start adding 4G and LTE, the weight and wind load impact on existing towers really has dramatically risen. And when I talk to operators around the world, I hear this over and over and over again. How can we reduce weight? How can we reduce wind load? It's a really significant concern. So one way to address that, of course, is to look at your LTE structural support. This chart just kind of shows an evolution of some of the structural things that we have done at CommScope to try to positively impact solutions for effectively reducing weight and wind load. So you can see here an illustration of the transition from 1 to 2G, you might have 2 square meter EPA, maybe 113 kilograms of weight. When you added 4G and the additional mounts and radio heads that are required, that bounced up to 350 kilograms. And your EPA went from 2 square meters to 6, a really significant impact. Now, we are in the process today of releasing a next generation mount system that we call our G2 series, aimed at engineering a mounting system specifically aimed at these 2 parameters of weight and wind load management. And we believe that we have come up with a solution to let us really pretty dramatically impact how existing cell sites can handle that additional weight and wind load with our Generation 2 mounting structures. So once we get beyond weight and wind load and those complexities, the next key thing is to find and eliminate interference. And there's 2 types, co-channel and adjacent channel. Now, I'm not going to give a whole lecture today on RF engineering and all that kind of stuff, but co-channel interference is a tough challenge to overcome, because your LTE carrier that you want and your LTE carrier and your interfering signal that you don't want basically sit right on top of each other. So resolving those types of interference issues require some pretty significant troubleshooting and problem evolution. Adjacent channel interference is a little bit different animal in that the wanted signal is really being interfered with by adjacent channels, and those type of interferers can be dealt with a little bit more in a straightforward nature with a technology that we call an interference mitigation filter, and I'll cover the interference mitigation filters in a little bit more detail later on. But what I'd suggest to you is this: as a user, or as you talk to users, is if we can get people to help describe what kind of interference it is, co-channel or adjacent channel, then we can more easily find the right solution, right? So we can help point, for example, in co-channel interference, many times you have to go to cell sites and move the pointing direction of antennas. And, so that's a pretty expensive thing, or to use digital filtering technology, that's another good way to do it. But it's a different type of animal and takes a different kind of solution. So it's important to identify it and then characterize which type it is. The next thing is avoiding passive intermod. Now, again, we have an entire day of training on passive intermod. So in this session, what I'll tell you is, passive intermod is simply unwanted signals that are created by nonlinearities in the RF path. Typically, they're created when you have rust or fasteners that aren't in intimate contact with other metals. So they create nonlinearities in the RF path. What's really important to realize, if you look at these 3 illustrations, that's the same antenna in all 3 illustrations. You can see in the first illustration with the antenna pointed at clear sky, you have beautiful passive intermod reading. That's fantastic. 166 dBc is theoretical. I mean, it's at the level of how good measurement equipment can be. Same antenna, a person walks up close to it in its physical field with keys or a phone or anything in their pocket, and that passive intermod level drops to 137 dBc. You get that same antenna pointed at something metallic. In this case, we've got it pointed at a fence, so it has reflected energy from that fence or that ladder coming back at it. That antenna performance looks like it's broken. So it's really important to realize that when we deal with passive intermod, it's not just the equipment, even though the equipment selection is very important. It also has to do with the frequency planning and installation practices. All 3 of those things, how to select the right equipment, how to deploy that equipment using appropriate frequency planning, and how to install that equipment using carefully thought through installation practices, are all really crucial elements of avoiding and mitigating passive intermod problems in your network. Okay, now the next slide starts to talk about beyond noise. We talk about interference, and this is where we get into discussions about antenna technologies very specifically, and very specifically where we talk about sculpting the RF energy as it comes out of the face of the antenna, to minimize overlapping RF energy from one sector to another sector, or from one cell site to the next cell site. Now, what we illustrate here in this diagram is that in GSM technology, the permitted cell site overlap was fairly forgiving. You could have up to 9 to 21 overlapping cells, basically depending on your BCCH and TCH channel applications, without having a significant impact on the user experience. Now, of course, the user experience was a voice experience, so it's just a more forgiving technology. With UMTS and CDMA, that overlapping area became significantly reduced. Why? Because in a CDMA or wideband CDMA technology, we have soft and softer handoffs. So those soft and softer handoff zones would more or less take away from the capacity of the radio. In LTE, which is even more interference limited, ideally we would have none. We would have no overlaps. You would have perfectly sculpted sector edges that would lay right next to each other with very little overlap, permitted maybe 2 or 3. So that's a really key consideration as we think through the right strategy for selecting the antenna technologies to go with a combined network of LTE and CDMA, or wideband CDMA, or LTE and GSM. What trade-offs need to be made, not only in the antenna selection, but in the pointing direction, in the position on the tower, in the down tilt strategy, where you tilt the elevation beam. All those have to be considered. So fortunately today, there's several new technologies that help us with sector sculpting. Certainly we are providing today 3 or 4 different technologies for sector sculpting, where we can take an existing 65-degree antenna and split that into 2 33-degree beams, and then create maybe a full cell site of 6-sector cell site. We have specialty antennas like the 5-beam antenna, absolutely a fantastic application for really hotspot urban areas where you need to push a lot of radio resource into a confined area where you have a big population of people. So those kind of sector sculpting solutions are really useful tools for adding capacity and densification and still minimize the amount of overlapping signal area in any given sector. This even applies in DAS. So if we go inside the building and we think about how DAS systems were deployed, DAS is typically designed in zones. So zone 1, zone 2, zones 3, zone 4. And in 2G technologies, it was very common, and is still very common today, to have one sector that covers all 4 zones. And as we moved into 3G, we started to split those zones into different sectors. But in LTE, what we're seeing is every zone more or less needs a different sector. Again, aimed at maximizing the capacity by limiting the amount of overlapping energy, therefore improving the SINAR. So you can see that really, that whole strategy applies even into in-building or venue type designs. So what does a 1 gigabyte per second macro cell look like in LTE in the future? This illustration came from a large operator in the Middle East, actually, a company named Ooredoo, that have given us a vision, their vision of how to build a macro cell with 1 gigabit per second capability. So what I've done next is try to lay out some building blocks to go from this vision to reality. And there's really several ways to get there. You can take what I would call a traditional architecture where the radios are at the bottom of the tower, or if it's a building mount in some kind of a shelter. You can take an approach of using traditional remote radio heads where the radio head is mounted on the tower, either closely behind the antenna or halfway up the tower, or whatever makes sense for your particular application. There's mixed architecture where you have some radio heads at the top of the tower, some radio heads at the bottom of the tower. There's certainly the integrated remote radio head that some of the large OEMs have offered to the industry. That's certainly an approach. And then, of course, the approach that comes from us, from CommScope, is what we refer to as our Andrews SiteRise solution, which, of course, I'll talk about later. So the enabling technologies to get there, and again, many of you hopefully are very familiar with these, but a key technology, diplexers, triplexers, dual band TMAs. Ultimately, what we want to do is minimize the weight and wind load at the top of the tower. And the fastest way to start to take weight and wind load in particular out of the top of the tower is to reduce the antenna count. And to do that, you use multi-band antennas. Well, with each of those multi-band antennas, then you have to think through how you feed the RF to it and from it. And that really is a diplexer or duplexer filter strategy. So all those things need to be considered. Then I talked earlier about interference mitigation filters. This is just a simple illustration of how, if, let's say that you detect an adjacent channel interference challenge at your site. And here's a good example of where you will find these type of interference issues. You may have an 850 megahertz operator, let's say in New York State, who has created interference in Canada, right, with too much power or overlapping power. That is a good example of where we detect a lot of these interference issues. So the idea then would be a custom designed interference mitigation filter, very specifically aimed at your frequency bands that you want to protect and your neighbors' bands that you want to protect yourself from. Design that in. It goes between the radio and the antenna, a very simple implementation. We've done tens of thousands of interference mitigation filters. Now, each one typically tends to be a little bit of a custom filter design because, again, your interference is kind of unique to you, so they require a little engineering up front, but again, we've done tens of thousands. A key technology is the ultra-wideband or the ultra-band antenna system, multiple ports. This particular one can launch up to 10 services out of one antenna face, each with independent electrical downtilt. Again, going back to what I'd said earlier about GSM, 3G, and 4G, all having different performance optimization characteristics. Really important that to realize that the downtilt level for 2G, if I think about all my years in the industry, for 2G, most 2G guys would downtilt their antennas about maybe 0 degrees to 2 degrees. For wideband CDMA, we would see tilt ranges in the 2 to 6 degrees. For LTE, it's not uncommon at all for us to see and have requests to do down tilting from 5 to 10 degrees. So the amount of down tilt in LTE tends to be a little bit more severe. Why? Because we're trying to mitigate cell-to-cell interference. And using that additional down tilt range is critical for that. Okay, so key again is the Helix fiber feed. This is the fiber optic cable that goes up to the remote radio head, a key ingredient in the design of any of these networks, as well as the RF jumpers are a critical consideration. And then a little bit about the SiteRise solution. This is what we think is the world's first pre-assembled tower top. What we believe is a very simplified approach that helps you be ready for the future. Fundamentally, what we've done with our SiteRise architecture or platform is take all the really complex work that happens at the top of the tower, move it to the bottom of the tower, or even better, into one of our factories, so that we can pre-assemble the antenna, all the RF connections, any type of filter, and the radio, pre-assemble it, pre-test it, and ship the entire kit already assembled, ready to go, so that all that needs to be done at your cell site is hoisted to the top of the tower. So what we've observed is that that really significantly reduces a lot of craft-induced errors, most specifically craft-induced PIM. And you can imagine if you're at the top of the tower and gale force winds, it's not an easy place to do high-quality work. So moving it to the bottom of the tower, or even better, as I'm illustrating here in this slide, doing that type of really high-quality, high-performance work in a factory-controlled environment really makes a big difference for simplifying logistics and getting to market faster. Ultimately, we recommend a systematic approach for LTE. First off, start with a good in-system frequency study. So it's really important to know which bands that you already own yourself can create intermod levels. And to the best of your ability, try to design your cell site so that you don't have those potential mixes on the same antenna. You know, if it's possible, you can design that away. Not always possible, but sometimes it is. So really do that frequency study up front. The second thing, have a good neighbor plan. Know what potential interference can come into your network from your neighbors, and what you can put as interference into your neighbors' networks. Really have kind of that overarching good neighbor plan of frequencies. Have a good strategy to find and mitigate noise and PIM. Again, ultimately the key to LTE success is improving the SINAR. So to have an ongoing program of finding and mitigating noise and PIM is really essential to success in LTE. Control interference by carefully selecting the antenna technology. Minimize overlapping patterns. Use tighter sectors where possible. Look carefully at deployment quality. Use a good design checklist of how to do installations. We highly recommend having your installer certified. And of course, we offer a number of training programs for installer certification. And of course, plan for the future. If possible, use antenna technologies that have very wide bandwidth. Try to design things so that, you know, who would have known 5 years ago that we would be putting radios at the top of the tower launching 2.5 gigahertz? I mean, so things change, and as much as possible, try to plan architecture that supports minimizing those future costs. Again, can't overemphasize how important it is to educate your installers, designers, your entire partner community. My experience is that LTE is a pretty complex technology, and the time has never been more important to have high quality training and a lot of collaboration. And speaking of collaboration, one thing I'd like to invite all of you who are participating in the webinar to take advantage of is our free LTE eBook. This is a little eBook that we've put together. It's a compilation of, I would say, the last 5 years of our practical experience in building LTE networks from an RF standpoint, implementation practical standpoint. It contains a lot of what I talked about today, available on your iPad, iPhone, Android, Amazon, and again, lots of great topics, digital format, easy to use, and we would love to have you download that, use it, and then come back with you if you have questions, comments, or seeking additional advice and commentary. So with that, I'll close this part of the presentation, and again, thank everyone for your attendance, and to Alliance for hosting us.
Thank you, Philip. That was an excellent presentation, very comprehensive. It's Lisa Travers from Alliance here. I'd like to invite everybody on who's still attending to, if you have any questions, you can submit them through the GoToWebinar console. In the meantime, I do have a couple of questions that are relatively general, and I think you did cover some of them. There's one question: how would you mitigate interference in a dense urban environment which is subject to a lot of reflections?
Right, that's a great question. It takes me back to a story, an actual engineering job that I did in San Francisco, where a roof of one of the nice restaurants there actually was covered in tin and was very reflective. And we ended up needing to change the antenna tilt. Right, so that's the first thing to look at if you have a high reflective environment. Look at your tilts and your bore sight pointing direction of your antennas and try to minimize the 3 dB point of the RF energy out of the antenna from being in the physical field, in the physical field of any metallic structure. This, again, is covered in great depth in our antenna theory class, which is available in our CommScope Academy. We've got a fantastic training class, about 6 hours of material on antenna theory and antenna applications. And one of the key topics that we talk about there is considerations in the deployment of RF to minimize those kind of problems.
That's great. Thanks, Philip. Actually, I would like to address something that I probably get from a lot of people. It's a question that hasn't been asked, but usually people are wondering, will we send out a copy of the presentation? And with your permission, I will send it out, a PDF of the presentation afterwards, as well as a link to where people can download your eBook.
We would love that.
Okay, great. There's one more technical question. It's just general again, more about cell density and how that affects power output and equipment choices.
Right, so keeping in mind, the first thing to always keep in mind is LTE is interference limited. So one of the things to consider is as if you deploy cell sites, let's say small cells, even though they have low power, let's say 300 milliwatt, the antenna pattern is still relevant. And if you use even a 300 milliwatt radio with an omnidirectional antenna or a very simple patch that has a very wide vertical beam width, our studies show that you still create a lot of interference. And it's a very simple problem to resolve. You can still use the small radio power, 300 milliwatts. We just highly recommend using a slightly more elegant antenna that still has some down-tilt beam tilting capability. Because in those dense urban areas, it's important to think through the fact that you really need to beam tilt to avoid interference from cell site to cell site. So that's probably the #1 consideration I'd recommend.
Okay, thank you. There was one question from someone online. How do you mitigate interference in heterogeneous, sorry, I'm not pronouncing right, heterogeneous networks, macro sites, microcells? Yeah,
excellent question, and it's very much similar to what I just talked about. So the heterogeneous network is really the combination of the macro cell layer and the small cell layer. And the real key question is, how do they hand off between each other, and how do they not interfere with each other? That's the key question. How do they not interfere with each other? Well, one clear way to handle that is with a frequency strategy. So it's not uncommon to think about it like this. You can use a design strategy of launching your macro with your low band, let's say 800 and 900 megahertz. Use that for your macro layer. And then as you build your small cell layer, use 2.5 gigahertz. Now that will give you some interference mitigation protection right there. But let's say you don't have enough frequency, or you don't have those frequencies, and you've got to do some sharing of frequency bands, the same frequency bands in both the macro and the small cell layer. In those cases, you have to think through the frequency pairs and allocations of frequency planning, right? So you've got to think through, where do I use my A block, my B block, and how do I divide up the frequency sets to minimize interference. And then you take an RF design approach of sector planning, right? So you can, for example, you can take your macro layers, change the azimuth pointing directions away from particular areas where you know you're going to put your small cell hubs, and that will help you minimize some interference from the macro to the small cell.
That's excellent. Thank you, Philip. I don't see any more questions, and we're getting close to the hour, so I think it's maybe time to say thank you very much for this fascinating, comprehensive presentation today. And I'm not sure if Gerard wants to add anything. But in any case, I will be sending out a follow-up email with a link to where you can download the presentation. And I have recorded this, so there will be an actual video that, if you want to watch it again or share it with some colleagues, you can do that afterwards. And there will be a link to download the book that CommScope has published. And thank you again for attending. Thanks again, Philip.
You're
welcome. Have a great day.